The real topic for today that we want to get into is about chemical bonds. When it comes to chemical bonding, there are really two primary processes that atoms can use to create compounds. So if we're going from individual atoms of elements to an overall compound, there are two primary ways that that can happen. But the way that they can happen comes from this idea that is the electrons that are going to be interacting with each other. So if you recall from earlier this week, we drew that model of the atom and we put that little tiny nucleus in the middle and we surrounded it with that big group of electrons in that cloud around that nucleus. Ultimately, the protons and the neutrons in that nucleus, because there are so many electrons between them and the outside world, really have nothing to do with chemical bonding. That nucleus identifies the atom, identifies the element, but it has nothing to do with its overall reactivity. It is the electrons that are going to drive that reactivity overall. And in order to answer that question of bonding and what drives certain elements to bond certain ways and other elements to bond other ways, the real question that we need to get into is, well, it might be helpful to look at this in the reverse. Neon, argon, krypton, xenon, radon. For the most part, those elements on the back end of the periodic table do not bond. And when they do, they make compounds so unstable that basically they would give anything to go back to being noble gases without any attachments. If we can understand why these guys don't bond, that might provide us a little bit of context for why all of these other ones do. So the real question is, why are these ones special? What do they do that's so different? And to answer that question, we have to understand a concept known as a valence electron. Now, in an atom, there are two different types of electrons. There are the electrons that are on the inside. We call those the core electrons. They occupy all of the energy levels kind of close to the nucleus. And as a result, they're kind of like the nucleus in the sense that they really aren't responsible for chemical bonding at all. The ones that are responsible for bonding are your outer electrons, the ones that are the closest to the outside world, the furthest away from the nucleus. These outer electrons, also known as valence electrons, are the ones that are ultimately responsible for chemical bonding. And so it is these that we have to concern ourselves with if we're going to answer this bonding question. The question before us, if valence electrons are all about what causes bonding, how do we even begin to know how many valence electrons that are in an atom? And the answer there is the periodic table. So if you have your tables on you, this would be a good time to do some adding. If the noble gases with their 8 valence electrons are unreactive, that must be the goal of chemical bonding. 8 electrons is sufficient to be stable. And so the point of any kind of bonding, whether it be ionic bonding or covalent bonding, is to get us to those 8 valence electrons. And if I can get to those 8 valence electrons, then I'm set, I'm stable. And either the atom is stable in the case of the noble gases, or the compound that is made becomes stable because the elements that make it up have now reached that optimal octet. And so this rule that we just shared here, this is known as the Octet Rule. The Octet Rule states that the whole purpose of bonding is to get those 8 valence electrons. When you have 8 valence electrons, your energy levels are full. Full energy levels are stable. Unfull, partially filled energy levels are unstable, at least in some kind of way. And as a result, those atoms, those elements are prone to bonding of some sort. Now, the question in front of us here is, what kind of bonding? And the best answer to that comes from evaluating what are known as Lewis dot structures. Lewis dot structures, their primary purpose is as a visual aid. They help us keep track of how many valence electrons are present, and they help us keep an idea of how those valence electrons are organized. Now, some rules for valence electrons and Lewis dots. In a Lewis dot structure, we are going to have an elemental symbol. For lack of a better term, we're going to use the X. And around that X, there are going to be 4 places where we can put Lewis dots on each of the 4 cardinal directions on each side of that symbol. Why 4? Well, as it turns out, if we get into deeper commentary on how that energy level is constructed, there are 4 different zones, we call them orbitals, where electrons can go in a given energy level in a valence shell. And for all intents and purposes, those 4 orbitals have roughly the same energy, and that's why the second rule applies. The dots are not allowed to double up until we have filled all 4 of those zones. Again, the thinking behind this is relatively simple. We have electrons. Electrons are negatively charged. 2 negatively charged objects generally don't like being in the same area as each other. They repel. So if we can put them in different areas, we can minimize their repulsion. That stabilizes the atom a little bit more. So let's take a look at some examples here. It's really where I wish the touch screen here was working, but we'll make do. So our first one, for lithium, we are going to draw in our dots. Now, lithium is element number 3. It is in group 1A, so it's going to have 1 valence electron. Now, there is no hard and fast rule for which way we fill those spaces first. So we can put that dot literally anywhere. We can put it on the right side, we can put it on the left side, we can put it on the upper or on the lower. Really doesn't matter. All that we're showing is that lithium has 1 valence electron and therefore 1 dot. Aluminum. Aluminum is in group 3A. 3 valence electrons. we're going to keep those electrons separate from each other. 1, 2, 3. To follow our rules. 3 valence electrons, 3 dots. All 3 dots are separated from each other. Oxygen. Oxygen's in group 16. Group 6A, 6 valence electrons. So I start by filling out 1, 2, 3, 4. Now that I have filled that space, 5 and 6 can come from any combination of doubling up. Again, yours doesn't have to look exactly like mine. It can be a little bit different. So long as you have 2 pairs of dots and 2 single dots, you're okay. Where you put those double dots and single dots really doesn't matter. For fluorine, fluorine F, that is a halogen. Halogens are in group 7A. 7 dots. 1, 2, 3, 4, 5, 6, 7. Again, where you put that single dot really doesn't matter. So long as it's 3 pairs of dots and 1 single dot, that's what ultimately makes the difference. Nitrogen. Nitrogen is in group 5A, group 15. 5 dots. 1, 2, 3, 4, 5. Neon. Neon is in group 18, group 8A, 8 valence electrons. It is a noble gas. 1, 2, 3, 4, 5, 6, 7, 8. All 8 valence electrons there around neon. Calcium. Calcium is in group 2, group 2A. 2 dots. Doesn't matter where you put them. They just need to be 2 single dots separated from each other. Silicon. Silicon's in group 4, 4A. 4 valence electrons. 1, 2, 3, 4. All 4 of those dots do need to be separate. All right, any questions about these examples? All right, I invite you to try some on your own then. Let's do rubidium and phosphorus and boron. All right, so work these out here on your own. 3 elements, find them on the periodic table, assign them the appropriate amount of dots, make sure you put the dots in the right places. All right, let's see how we did. Rubidium. Rubidium is in group 1A. It is an alkali metal. It should only have the 1 dot. Again, that dot can be on any of the 4 sides, just so long as there's only 1 of them. Phosphorus. Phosphorus is in group 5A. 5 valence electrons, 5 dots. 1, 2, 3, 4, 5. Again, the placement of that double dot is not super important, just so long as there's 1 double dot and 3 single dots. Boron is in group 3A, 3 valence electrons, like so. And that's all it is.